the atom in the periodic table. So in the last lecture, we looked at the history of how we developed this idea of the atom and what makes up an atom of any given element. So if you remember, in our current model of the atom, we have the proton and the neutron, about approximately the same size and mass. They're located in the nucleus, which is in the center of our atom, around which we have this electrons density. So there's electrons around these nuclei. So now let's talk about how we then can classify our shorthand notation for these atoms and connect individual atoms to different element types. So we have developed this shorthand notation where we abbreviate each element by an elemental symbol. Here I'm showing that symbol as an X. And then on the left-hand side, in the subscript, we put the number of protons, so which we abbreviate capital Z. So this atomic number, the number of protons, is how we actually identify an element based on its number of protons. So if the number of protons changes, the identity of the element changes. So for example, hydrogen has 1 proton, it has a Z number of 1. Something like carbon has 12 protons, its Z number is 12. Every time we change the number of protons, the identity of that atom changes. Superscript on the right side, we put the mass number. So we said that the neutrons and the protons are approximately the same size, so that the atom can be approximated by the total number of those nuclear particles. So we call that the mass number A, the number of protons plus the number of neutrons. An interesting thing is that these elements themselves, while they might all have the same number of protons, they can have different numbers of neutrons, which lead us to this idea of an isotope. Something that behaves very, all elements, it's the same type of element, it just has a different number of neutrons. So its mass number, A, is going to be different. So if we look at hydrogen, for example, there's 3 naturally occurring isotopes of hydrogen. There's the hydrogen we think of, which has 1 proton, no neutrons. Deuterium, which is again a isotope of hydrogen, it has 1 proton, 1 neutron, so it has a mass number of 2 in the middle here. And then the third one, this tritium, which has 1 proton and 2 neutrons, right, which we abbreviate T. Right, we see the same thing occurring also in a wide variety of elements. In fact, most elements have at least some different isotopes. Another common example is uranium, 235 and 238. Right, so let's look at some examples and extract this kind of information. So if we look at magnesium here, we see that it has a mass number of 24 and a proton number, atomic number of 12. So the proton numbers would be 12. The neutrons would be the 24 minus 12 to get equal to 12 also. And then the number of electrons, if this is a neutral atom, which we see it is, then the number of protons has to equal the number of electrons, so we get that charge balance, the total charge of 0. Again, if we look at lead, 208, has a mass number of 208, proton number of 82, the number of protons again 82, the number of neutrons then would be the 208, the mass number, minus those number of protons, 82, to give us 126. Again, we have a neutral atom, so our electrons would be 82. And we can carry that same process out for barium here at the bottom. Again, from just this information, the number of protons and the mass number, we can calculate all of those subatomic species. All right, so we've spent the last 2 lectures now, lecture and a half, talking about this atomic world and building atoms to make molecules in a very microscopic, small level. But we exist in a very macroscopic world, and we work with grams. So in order to make that transition, we're going to have to do a couple things. And the first is when we talk about this atomic mass, we have to give some mass to those values. So one way we can think about atomic mass is what we call atomic mass units, or AMUs. And we've defined an AMU as being the mass of 1 atom of carbon-12. So it's an isotope of carbon. Has the mass of exactly 12 AMUs. Right? So every other isotope or atom we look at, we compare it to that definition. So for example, hydrogen Regular hydrogen with only the one proton has then atomic mass of 1.008 AMUs. Oxygen 16 has 16 mass of 16 AMUs, and then sodium 23, that isotope of sodium, has a mass of 22.99. Right, so now we can then look at that atomic symbol and know information about how much it weighs based on this definition. I would typically say that chemists are by sort of nature lazy, so we try to come up with these shorthand notations and sort of cheat sheets along the way. The most common is the periodic table. Right? So the periodic table lists all our known elements. Some are naturally occurring, most of them are. Some of them are man-made. The ones at the lower end, the higher atomic numbers, are only are present in the laboratory. They don't find them in nature. We group these together based on similar properties. So the elements that are placed next to things that behave fairly similar to each other. And on the periodic table we have two different things. The rows we can call periods, the columns we can call groups. So those elements we say have a very group-like behavior. So everything in the same column is going to behave very similar. And then we'll look at trends later on as we move across the periodic table. So we group these things sort of as they behave similarly. So if we look at one side of the periodic table, the left side, we see that we get those are a group of nonmetals, things like carbon, oxygen, fluorine, bromine. All the things in yellow here are nonmetals. Next to those, in sort of the staircase, that light green, those are metalloids. Everything on to the left of those are going to be metals. So on the left side of the periodic table we have metals, on the right side nonmetals, in between those the metalloids. We've also come up with some names for some of these groups. You can see here, so the far left, that first group 1A for example, we call those the alkali metals. 2A, the one right next to it, we call the alkali earth metals. If we go the group in between there, we call transition metals. On the very right side, we see that we have in group 7A the halogens, things like fluorine, chlorine, bromine are in the halogen group, and then the very end there are the noble gases, helium, neon, argon, those we call the noble gases. So then if you looked on the periodic table, if we zoom in on one of those cells, we see that all the information, or a large amount of information we have about that element is present there. We have the atomic symbol. So for carbon, in this case, its elemental symbol is C. Above that, typically we put the atomic number, that number of protons. And then below that, we put some indication of atomic mass. So this atomic mass is slightly different than the AMUs we were talking about per one isotope. These atomic masses listed on the periodic table are a weighted average of all naturally occurring isotopes. So we'll go through how we do that in a second. So all the numbers we see here aren't for a specific isotope. It's a weighted average for every species. So if we look at this weighted average in terms of chlorine, chlorine has two naturally occurring isotopes, the chlorine-35 versus the chlorine-37. The chlorine-35 accounts for about 75.78% of all naturally occurring chlorine, and it has an atomic mass of 34.696 AMUs. The 37 chlorine accounts for the remainder, the 24.22%, and it has an atomic mass of 36.966. So if we weight that average, we're going to take the abundance times the mass, add those together. So if we look at for chlorine, we take the 0.7578 times the mass of that chlorine-35, 34.696 AMUs, and add that to the 0.2422 times 10 to the times the 36.966 AMUs to give us a weighted average of 35.45, which is the number we see appearing on the periodic table. So we have to make that distinction. It's very unclear sometimes, but the one on the periodic table is all the naturally occurring isotopes. When we talk about atomic mass, we're talking typically about the A value is for that specific isotope, the number of protons and neutrons. Right? So in the next lecture, we're going to take this information off the periodic table and begin building compounds and talking about how we name those and how they interact. But because of that, you're going to have to start learning the periodic table. So I suggest you start familiarizing yourself with the periodic table, the first 18 or so elements, start to learn their atomic symbols, where they are located, metal, non-metal, because that'll come in handy when we start doing the naming process later.
I don't get it!